Hello. In this part of the lesson, I'm going to talk about solving quadratic equations. We talked about this last week, solving quadratic equations using the zero product principle. This week, I'm going to talk about solving quadratic equations using what we call the square root property. And I'm also going to talk about different types of solution sets to quadratic equations. So let's begin by talking about the square root property. The square root property looks a little scarier than it really is. It says that u squared equals k if and only if u equals plus or minus the square root of k. In this statement of the property, we usually use u to represent an algebraic expression and k to represent a real number. Remember, when we say that u equals plus or minus k, what we're really saying is that u can equal the positive square root of k, which we usually just refer to as the square root of k, or u can equal the negative square root of k. So for example, x squared equals 7 if and only if x equals plus or minus the square root of 7. X can be the square root of 7, or x can be the negative square root of 7. Similarly, t squared equals 9 if and only if t equals plus or minus 3. Where did this plus or minus 3 come from? It came from the fact that t has to equal plus or minus the square root of 9, and the square root of 9 is 3. Now usually we only use this property in one direction. For example, if we have the equation x plus 4 quantity squared equals 8, we can move toward our solutions if we use the square root property and say that x plus 4 has to equal plus or minus the square root of 8. Let's see several examples of this. Let's solve the equation x minus 2 quantity squared equals 81. So as always, I begin by writing down the given equation. And what I'm going to do next is I'm going to use the square root property. And the square root property says that x minus 2 must equal plus or minus the square root of 81. Well, I know what the square root of 81 is. It's 9. And this plus or minus is telling me that I really have two equations to solve. X minus 2 equals positive 9, or x minus 2 equals negative 9. These are two simple linear equations. Adding 2 to both sides of the equation on the left, I get that x equals 11. And adding 2 to both sides of the equation on the right, I get that x equals negative 7. So it looks like I have two solutions, 11 and negative 7. But I bet you know what I'm going to do next. I'm going to check. So if x equals 11, then x minus 2 quantity squared, I'm going to do a little arithmetic in my head. If I replace x with 11, I'm going to have inside the parentheses 11 minus 2, which is 9. So x minus 2 quantity squared is 9 squared, which really is 81. How about if x equals negative 7? Well, then the variable expression, x minus 2 squared, again doing a little arithmetic in my head, negative 7 minus 2 is negative 9, so the variable expression becomes negative 9 quantity squared, and negative 9 times negative 9 is also positive 81. Both my solutions check. So let's state our conclusion. The solutions are 11 and negative 7. Let's solve this equation. The quantity 5t plus 4, when it's squared, results in 25. Well, there's two ways that can happen. 5t plus 4 can be the square root of 25, or negative the square root of 25. That's called the square root property. So I have two equations. 5t plus 4 is 5, because 5 is the square root of 25, or 5t plus 4 is negative 5, because negative 5 is the negative square root of 25. I'm going to solve both these linear equations in my head. On the first equation, if I subtract 4 from both sides, I'll have 5t equals 1. And then when I divide both sides by 5, I'll have t equals 1/5. On the second equation, when I subtract 4 from both sides of the equation, I'll have 5t equals negative 9. And then when I divide both sides of the equation by 5, I'll have t equals negative 9/5. Now, you might have more luck and more success if you do write the middle steps down. 5t equals 1 or 5t equals negative 9. And if you have more success writing down those middle steps, go ahead and do it. I'm just encouraging you to experiment and see if you can solve these linear equations in your head. But you know what we need to do? We need to check. So if t is 1/5, then 5t plus 4 quantity squared, this time I think I'm actually going to show the arithmetic. I need to take 5 and multiply it by 1/5 plus 4 and square that quantity. Well, 5 times 1/5 is 1, and 1 plus 4 is 5, so this is 5 squared, which really is 25. So 1/5 checks as a solution. How about if t is negative 9/5? Then our variable expression, 5t plus 4 quantity squared, that becomes 5 times negative 9/5 plus 4 quantity squared. Looking at 5 times negative 9/5, I could pull out a factor of 5 over 5, and all that would leave behind is negative 9 in the numerator, and negative 9 plus 4 is negative 5. So this is the square of negative 5, which is also 25, which is what we wanted 5t plus 4 quantity squared to equal. So this solution checks as well. So the solutions are 1/5 and negative 9/5. Ooh, look at this equation. Please solve x squared equals 16. This equation seems pretty simple compared to the earlier examples. I wonder why I have this. Well, I have this because I want to make sure that you don't develop a really bad habit. No square rooting. Please. What do I mean by square rooting? Well, look at this proposed solution. X squared equals 16. Let's square root both sides, and then we're left with x equals 4. Well, what's wrong with this? Well, let me count the ways. The first thing that's obviously wrong with it is that we don't have both of our solutions. There's two numbers I can square that give me 16, both positive 4 and negative 4. Now, an easy way to fix that, you might think, is, well, let's just put a plus or minus sign in front of our 4. Then I do have both solutions. But there's still problems with square rooting both sides. Writing this step still reinforces two very common misconceptions. The first misconception that writing this step reinforces is that the square root of 16 is both positive 4 and negative 4. That's not true. By definition, the square root of 16 is a non-negative number. So the square root of 16 is 4. End of story. The other misconception that this reinforces is even more dangerous, and that's that the square root of x squared equals x. Now, it seems at first blush that that must be true, but that is not necessarily true. Again, let's think about the fact that there's two numbers that we can square that gives us 16. I can square negative 4 and get 16. Consequently, the square root of negative 4 squared is the square root of 16, and we just discussed the fact that the square root of 16 by definition is positive 4. So check it out. Here we have the square root of negative 4 squared, and that's equal to positive 4. So this definitely is not a true statement that the square root of x squared equals x. Consequently, we do not want to be square rooting both sides. So let's get out our eraser, and let's get rid of this square rooting both sides step, and let's put the proper step in the middle. And the proper step in the middle is using the square root property that says that x equals plus or minus the square root of 16. And since the square root of 16 is 4, x equals plus or minus 4. So our solutions are plus or minus 4. All righty, let's look at this equation. 8t squared minus 44 equals 0. I do not have a perfect square equals a number, so I can't use my square root property yet. So the first thing I need to do is use other properties of solving equations so that I do have a perfect square equals a number. The only perfect square I'm seeing is t squared. So my first objective is to isolate t squared. Adding 44 to both sides of the equation, 8t squared equals 44. Dividing both sides of the equation by 8, t squared equals 44 over 8. And 44 and 8 are both evenly divisible by 4, so I can reduce this fraction to 11 over 2. So using the square root property, t must be plus or minus the square root of 11 over 2. Now, I know that you're going to check this answer on your paper, but I also know that you're a student and you're probably going to look at the answer in the back of the book. And when you look in the back of the book, you're not going to see this answer. Remember something that Ann just showed you called rationalizing the denominator? Most books on this type of exercise, when they get an answer like this, they rationalize the denominator. So let's go ahead and rationalize the denominator. I'm first going to rewrite this fraction as the square root of 11 over the square root of 2. And to rationalize the denominator, I need to introduce another factor of the square root of 2 to the denominator. But if I want to get back the same quantity that I originally had, I need to multiply overall by 1. So the numerator also needs to be multiplied by the square root of 2. So now I have in the numerator the square root of 11 times 2, which is the square root of 22. And in the denominator, I have the square root of 2 times the square root of 2, which is 2. That's the whole reason I multiplied by the square root of 2. So let's check our answers. Let's check plus or minus the square root of 22 over 2. This time, I can get a 2 for 1 check. When I square the square root of 22 over 2, that's the product of two factors of positive square root 22 over 2. When I square negative square root of 22 over 2, that's the product of two negative square roots of 22 over 2. But when you multiply two negative numbers, the result is positive, just like when you multiply two positive numbers. So the product of these two negative numbers is the same as the product of two factors of positive radical 22 over 2. Look at the right side of these two equations. They're identical. Consequently, the left sides are also equal to one another. Now, when I look at my equation, the only occurrence of the variable is a squared occurrence. And since the square of both of these numbers is the same, I can check both of these solutions at the same time. So if t is plus or minus the square root of 22 over 2, then 8t squared minus 44 is going to be 8 times the square root of 22 over 2 quantity squared minus 44. So this is going to be 8 over 1 times, using one of my properties of exponents, I can distribute the square to both the numerator and the denominator of the fraction. So this is 8 over 1 times the square root of 22 squared is 22. That's the whole purpose of being the square root of 22. 2 squared is 4. And I'm still subtracting 44. So let's see. 4 goes into 8 2 times, and 2 times 22 is 44. And last time I checked, if you take away 44 from 44, you get 0, which is what I wanted 8t squared minus 44 to evaluate to. So I can go ahead and say that the solutions are plus or minus the square root of 22 over 2. How about y squared equals 12? Well, if y squared equals 12, we have this swell new property called the square root property. Y equals plus or minus the square root of 12. But when I look in the back of the book, that's not what the answer says. How come? Well, because 12 is evenly divisible by a perfect square. What perfect square goes into 12 evenly? 4. So I can rewrite 12 as 4 times 3, And by one of my properties of square roots, I know that this equals the square root of 4 times the square root of 3, and the square root of 4 is 2. So this is equivalent to plus or minus 2 square roots of 3. Let's check. Can I do a 2-for-1 check? You betcha. My numbers are opposite, and the only occurrence of the variable is a squared occurrence of the variable. Squaring opposite numbers results in the same result. So, if y is plus or minus 2 square root of 3, then y squared is 2 square roots of 3 squared. If I put the negative number inside the parentheses, since I'd have 2 negative factors, the product will come out positive anyway. Using my products to power exponent rule, this is the same as 2 squared times the square root of 3 squared. 2 squared is 4. The whole purpose of being the square root of 3 is that if you square it, the result is 3, and 4 times 3 is 12, which is what I wanted y squared to be, so my answer checks. So the solutions are 2 square root 3 and negative 2 square root 3. On the last example, when I stated my conclusion, I just said plus or minus the square root of 22 over 2. Here, I wrote the two solutions down individually. I'm kind of letting you know that it's okay to write your conclusion either way. All right, x minus 9 quantity squared equals 82. I have a property. You know what it's called? It's called the square root property. And the square root property says if this quantity squared equals 82, then the quantity that's being squared has to equal plus or minus the square root of 82. Before I solve for x, I need to ask myself, does the square root of 82 simplify? Is there a perfect square that divides into 82? Well, let's think about that. 2 goes into 82 how many times? 41. Well, 41 is a prime number. And one thing that's definitely true about a prime number, it is not a perfect square. Because if it was a perfect square, there'd be 2 non-1 factors that divided into the number. So that's how a long way of saying that the square root of 82 doesn't simplify. So what are my two equations? X minus 9 equals the square root of 82, or x minus 9 equals negative square root of 82. Now, both of these equations I can solve by adding 9 to both sides of the equation. So I'm left with x equals 9 plus the square root of 82, or x equals 9 minus the square root of 82. Now, you might be wondering, why did I choose to write the 9 first? Usually, when we're writing down expressions that have both a square root and an integer, we write the integer first so that there's complete lack of ambiguity about what is underneath the square root and what is not underneath the square root. Let's check out something else about these solutions. They look very similar. The only difference is in the solution on the left, there's a plus sign between the two terms, and in the solution on the right, there's a subtraction sign between the two terms. Consequently, I could, if I chose, write this in a more abbreviated form, that x equals 9 plus or minus the square root of 82. And if I looked up a few lines, I see that I actually could have seen that right here if I had just in this form gone ahead and added 9 to both sides of the equation. Consequently, that is what I'm going to do in future examples. But you know, we need to check. Can I do a 2-for-1 check? No way, Jose. Neither of the conditions for a 2-for-1 check are satisfied. The occurrence of the variable is not squared. It is squared after I subtract 9, but just the variable itself is not squared. Also, these two numbers are not opposite numbers. The square root of 82 is a little bit bigger than 9 because 9 squared is 81. 9 plus a number a little bit bigger than 9 is bigger than 18. 9 minus a number that's a little bit bigger than 9 is just a teeny tiny bit less than 0. These numbers have opposite signs, but they are not opposite numbers because their absolute values are not equal to one another. So let's go ahead and check these one at a time. If x equals 9 plus the square root of 82, then the quantity x minus 9 squared is 9 plus the square root of 82 minus 9, that quantity squared. Because of the commutative property of addition and the fact that subtracting 9 is the same as adding negative 9, I can just add the 9 and the negative 9. That adds to 0, and I'm just left with the square root of 82 squared, and the square root of 82 now is happy as a clam because it's just had its day. It's been squared. So it can fulfill its manifest destiny and become 82. Hey, let's check out the other solution. If x equals 9 minus the square root of 82, then x minus 9 quantity squared, that is 9 minus the square root of 82 minus 9 quantity squared. Again, because of the commutative property of addition and the fact that subtraction is the same as adding a negative, I can add the 9 and negative 9. That gives me minus the square root of 82 quantity squared. Squaring a negative number results in a positive number, so this also is 82. Both answers check. The solutions are 9 plus or minus the square root of 82. All right, let's work this problem. 3x plus 17 quantity squared equals 45. Square root property. 3x plus 17 equals plus or minus the square root of 45. 45 is evenly divisible by 9, and 9 is a perfect square. So I want to think of 45 as 9 times 5, and one of our square root rules says, therefore, we can rewrite this square root as the square root of 9 times the square root of 5. So this is plus or minus 3 times the square root of 5. Let's do a 2-for-1 solving of our two solutions. If 3x plus 17 equals plus or minus 3 square roots of 5, 3x has got to equal negative 17 plus or minus 3 times the square root of 5. And when I divide both sides by 3, I'm left with negative 17 plus or minus 3 times the square root of 5, all divided by 3. Now, before I check, I want to talk about a common boo-boo that you want to avoid. And that is looking at this expression, seeing a 3 in the numerator and denominator, and dividing them out. Are these two expressions equal to each other? Well, I don't think so. And one way that I can see that they're not equal is just focusing on the plus term in the numerator. If I have negative 17 plus 3 square roots of 5 divided by 3, if I want to break this up into two terms, not one single fraction, both terms need to get a denominator of 3. Now, 3 is a factor of the numerator of the second fraction, so the 3's do divide to 1 in the second fraction. But check it out. I have negative 17 thirds plus the square root of 5, and that definitely does not equal negative 17 plus the square root of 5. So this is definitely incorrect. When you're wondering whether or not you can simplify fractions that look like this, the real question you have to ask yourself is 3 a factor of the numerator, negative 17 plus 3 square roots of 5? The reason you need to ask yourself that question is because if you can factor 3 from the numerator, then because this expression equals 3 over 3 times a plus b over 1, if 3 is a factor of the numerator, 3 over 3 does divide to 1, and we are just left with a plus b. But is 3 a factor of negative 17 plus 3 square roots of 5? I don't think so. 3 does not evenly divide into 17. Since 3 is not a factor of this numerator, we cannot simplify this fraction. So let's check. I'm going to check 1 and leave the other check for you. If x equals negative 17 plus 3 square roots of 5, all divided by 3, then our variable expression, quantity 3x plus 17 squared, becomes 3 times negative 17 plus 3 square root of 5 all over 3 plus 17 quantity squared. Here, I can factor out 3 over 3 from the fraction. When I do that, all I leave behind is the numerator of the second fraction in the first term, which is a long way of saying I leave behind negative 17 plus 3 square root of 5. I still have my plus 17. This is all squared. The 17s add to 0, so I'm left with 3 square root of 5, quantity squared. Using my products to power rule, this is 3 squared times the square root of 5 squared, which is 9 times 5, which is 45, which is what I wanted 3x plus 17 quantity squared to equal. So this checks. So I'm leaving it to you to check the other solution. When you verify that the other solution does check, don't forget to write down your conclusion, that the solutions are negative 17 plus or minus 3 square root of 5 all over 3. I want to talk just a little bit about different types of solution sets you get to quadratic equations. Let's look at 3x squared plus 12 equals 0. Well, so far, I don't have a perfect square equals a number. So that's my first objective. Let's isolate x squared. 3x squared equals negative 12, so x squared equals negative 4. What real number can you square and get negative 4? Well, when I think about this, the square of a positive number is positive, the square of a negative number is positive, the square of 0 is 0. I'm out of real numbers. There is no real number that I can square that gives me negative 4. So what's up with this equation? What's up is this equation has no real number solutions. Not every equation has a real number solution. We just shown that. How about this equation? 5t plus 32 quantity squared equals 0. Well, one way we could solve this equation is we can think of this as the product of two factors of 5t plus 32 and equals 0 and use the zero product property. If two factors of 5t plus 32 multiply to 0, one, or in this case both factors, has to equal 0. We also can solve this using the square root property. If 5t plus 32 quantity squared equals 0, 5t plus 32 has got to equal plus or minus the square root of 0. What number do you square that gives you 0? Well, that would be 0. What's negative 0? Well, that also would be 0. All I'm hearing is 0, 0, 0. 5t plus 32 equals 0. Solving this in my head, I get t equals minus 32 fifths. If you're not seeing where I'm getting that from, write the step down in the middle, and I'm sure you will see where I'm getting this solution from. So now we need to check our solution, negative 32 fifths. But I'm getting a signal that I'm about to run out of time, so I'm going to let you check this solution. And once you've checked the solution, go ahead and write your conclusion, that the solution is negative 32 fifths. Now, we've seen several examples of quadratic equations with two solutions. We've just now seen a quadratic equation with one solution and a quadratic equation with no real number solution. These are the three possibilities when you're looking for solution sets to quadratic equations. Quadratic equations can have two solutions, exactly two solutions. Quadratic equations can have one solution, exactly one solution. Or quadratic equations can have no solutions, at least if you're looking for real number solutions. In later classes, you're going to learn about other types of numbers, and when you start incorporating these other types of numbers, it turns out that a quadratic equation always has either exactly one or exactly two solutions. But over the real numbers, quadratic equations can also have no solutions. So now I'm going to turn this over to Kandace so that she can work some application problems with you.
Hi, in the last part of the lesson, I'm going to look at some applications. I'm going to start by looking at the Pythagorean Theorem and doing some examples. And then I'm just going to do a bunch of other examples. So what is the Pythagorean Theorem? In a right triangle where A and B represent the lengths of the legs and C represents the length of the hypotenuse, A squared plus B squared equals C squared. Let's look at an example of this. Find the length of the hypotenuse of a right triangle with legs of lengths 3 inches and 4 inches. Well, we've got a right triangle. One of the legs has a length of 3 inches and the other has a length of 4 inches. We're trying to find the length of the hypotenuse. So let's let D represent the length of the hypotenuse in inches. Then the Pythagorean theorem tells us that 3 squared plus 4 squared equals D squared. So 9 plus 16 equals D squared. So 25 equals D squared. Then the square root property tells us that D must equal plus or minus the square root of 25. So D must equal plus or minus 5. Well, let's think about what D represents. We define D to be the length of the hypotenuse in inches. A length can't be negative. So in this case, it doesn't make any sense to choose D equals -5. The only answer that makes sense here is +5. Let's make sure that this does actually check before we write down our solution. We already figured that 3 squared plus 4 squared, the sum of the squares of the legs, is 9 plus 16, or 25. The only thing left to check is that the right-hand side of the equation, D squared, is also 25. Well, if we choose D equals +5, 5 squared is indeed 25. So let's write our conclusion. The length of the hypotenuse is 5 inches. Well, there's another way that we can think about the Pythagorean theorem, and I don't think this is the picture that comes immediately to most people's minds. I know in my case, when I learned the Pythagorean theorem, this never would have come to my mind. So let's think about a triangle, and let's say that one of the legs has a length of 3. So here we've got 3 units along the one leg, and what I've done here is built a square off of the leg. So this square is 3 by 3, 9 square units. Now let's say the other leg has a length of 4 units, and let's build a square off of this. So now this square is 4 units by 4 units. We have 16 square units in this square. Well, the Pythagorean theorem tells us that 3 squared plus 4 squared is going to give us the hypotenuse squared. So our hypotenuse, as we just figured in our last example, would have to have a length of 5 units. The square that we build off the hypotenuse would be 5 units by 5 units, so 25 square units. These 9 square units plus 16 square units add up to our total of 25 square units. Let's look at another example. Let's find the length of the remaining leg of a right triangle with a leg of length 5 feet and hypotenuse of 13 feet. So here, one of the legs of the triangle is 5 feet. The hypotenuse is 13 feet. We're looking for the length of the remaining leg. So let's let D represent the length of the remaining leg of the triangle in feet. So the Pythagorean theorem tells us 5 squared plus D squared must equal 13 squared. To solve for D, well, first I'm going to square 5 and square 13. That gives me 25 plus D squared equals 169. Then I'm going to subtract 25 from both sides of the equation. So D squared equals 144. Using the square root property, we know that D must equal plus or minus the square root of 144. So D must be plus or minus 12. Again, we let D represent a length here, so -12 doesn't make any sense in this case. So we need to choose D equals +12. And we need to make sure that this does actually fit. So as a quick check, 5 squared is 25. If D is 12, 12 squared is 144. 25 plus 144 is 169, and 13 squared is 169. So this checks. So let's go ahead and write our conclusion. The remaining leg of the triangle There are actually some things called Pythagorean triples that show up a lot on standardized tests. We just looked at a couple of them. 3, 4, 5 is called a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. 5, 12, 13 is another Pythagorean triple. 5 squared plus 12 squared equals 13 squared. There are lots of Pythagorean triples. These are just called Pythagorean triples because you get integers for the lengths of the legs as well as the length of the hypotenuse. So now let's find the length of the diagonal of a rectangle with width 6 inches and length 11 inches. So we're looking at a 6-inch by 11-inch rectangle, and we're interested in the length of the diagonal. One thing I notice about this picture is I could look at just half of the picture and I'd have a right triangle, in which case I could apply the Pythagorean theorem. So let's just concentrate on half of the picture. Now we have a right triangle with legs of length 6 inches and 11 inches. And we're looking for the length of the hypotenuse. It's still the diagonal of our rectangle, so I'm going to define it that way. Let d represent the length of the diagonal in inches. Then the Pythagorean theorem tells us that 6 squared plus 11 squared equals d squared. So we have 36 plus 121 equals d squared. So 157 equals d squared. Now the square root property tells me that d has to equal plus or minus the square root of 157. So I have d equals plus or minus the square root of 157. Again, d is representing a length, so negative square root of 157 doesn't make any sense here. One thing I should be asking myself, since I'm leaving my answer in exact form, is can I simplify the square root of 157 in any way? Well, are there any perfect square factors of 157? Think about it for a little while. 157 isn't divisible by 4, 157 isn't divisible by 9, 157 isn't divisible by 16. And you can keep going through some of the perfect squares. You're going to see that there is not a perfect square that divides evenly into 157. In fact, I think 157 is a prime number. So let's go ahead and make sure that our answer actually checks so that we can write our conclusion. So we already figured out that the sides of the rectangle, when we square them, 6 squared plus 11 squared, and add them together, add to 157. Well, we're choosing d equals the positive square root of 157, and when we square the square root of 157, indeed, we get 157. So this checks. So now I can go ahead and write my conclusion. The length of the diagonal of the rectangle is exactly, I didn't approximate here, the square root of 157 inches. Here's a more real-life application. Andrew drives due north 8 miles and turns and drives due east 12 miles. Find the distance that Andrew is from his original location. So let's think about what's happening here. Andrew drives due north 8 miles. Then he turns and drives due east 12 miles. So let's label this. We have 8 miles due north and then 12 miles due east. Find the distance that Andrew is from his original location. So we're looking for this distance. Since he drove due north and then due east, these paths meet at a right angle. So I'm looking at a right triangle type problem, and I can apply the Pythagorean theorem. So I'm looking for this distance. I'm going to let d represent the distance that Andrew is from his original location. And here we're measuring in miles. So the Pythagorean theorem tells me that 8 squared plus 12 squared equals d squared. So 64 plus 144 equals d squared. So 208 equals d squared. The square root property tells me that d is going to be plus or minus the square root of 208. Once again, d is representing a length. It's a distance this time. So the negative square root of 208 doesn't make any sense. The only answer that makes any sense in this real-life application is the positive square root of 208. In this case, since I'm looking at a real-life application, Andrew driving, I'm going to go ahead and approximate the answer. So I'm going to pull out my calculator and figure out an approximation for the square root of 208. So if I take the square root of 208, I get about 14.4. So d is approximately plus or minus 14.4. We already discussed, though, the only answer that makes sense here is the positive value. So d is approximately positive 14.4. Let's go ahead and check this. We already said 8 squared plus 12 squared simplified to 208. Well, what happens when I square 14.4? Well, let's pull out the calculator again to do this calculation. 14.4 squared, well, I was hoping it was 208. But remembering that 14.4 was only an approximation, it makes sense that I'm only getting an approximation for 208. 207.36 is pretty close to 208. So let's go ahead and write our conclusion. Andrew is about 14.4 miles from his original location. Notice I wrote the word about in my conclusion. That's indicating I made an approximation. I could also have written approximately. Remember, we usually approximate answers for applied problems. This, to me, seemed like a real-life application, and leave answers in exact form otherwise. Now we're going to look at some more examples. The length of Kandace's swimming pool is to be 3 times the width. If the depth is to be a constant 4 feet and the volume is to be 4,800 cubic feet, find the dimensions of the pool. So we're looking at a swimming pool with an unknown width, but we do know that the length is 3 times the width, and we do know that we have a constant depth of 4 feet. So in this case, I need to go ahead and define my variable. I already have it written for me on the drawing, but we have this variable w. And w in this case is representing the width of the swimming pool. And we're measuring in feet. So how are we going to figure out what this width is going to be? We have to think back to some of the formulas that we know from geometry. And the formula for finding the volume of a rectangular solid is that the volume is the length times the width times the height. If you don't remember that, that's okay. You can look that up in your textbook, and you should be able to find that. So if W is the width of the swimming pool, we know that the volume is going to be length times width times height. So 3W times W times 4. Well, we were given that the volume of the swimming pool is going to be 4,800 cubic feet. So here we can say that 4,800 is equal to 3 times W times 4 simplifies to 12W squared. Solving for W squared by dividing both sides of the equation by 12, I get 400 equals W squared. Applying the square root property, I know that W must equal plus or minus the square root of 400. So W must be plus or minus 20. W is representing the width of the swimming pool, so negative 20 doesn't make any sense here. Let's make sure that positive 20 actually does work. So I still need to check my result. If W equals 20, then we know that the length, 3W, is going to be 60. And the volume is 60 feet times 20 feet times 4 feet. 60 times 20 times 4 is 1,200 times 4, which is 4,800. And we multiply feet by feet by feet, we get feet cubed, which is cubic feet. And the volume of the pool was supposed to be 4,800 cubic feet. So this does check. So I can go ahead and write my conclusion. The dimensions of Kandace's pool are 60 feet by 20 feet by 4 feet. Now let's look at another application. Uncle Jeb's potato field is circular. He's going to construct a watering device with pipe in a line extending from the center of the field to the edge of the field. The pipe is to be set up on wheels so that it can rotate around the field and cover the entire field with water. If the area of the field is 7,728 square feet, what length of pipe does Uncle Jeb need to buy? So we've got the circular field, and we're going to buy this piping to water the field. So this is going to rotate around and cover the whole field. We know that the area of the field is 7,728 square feet. We want to figure out what length of pipe Uncle Jeb needs to buy. So we're interested in what is the length of this pipe. So let's go ahead and define R as the length of pipe. Uncle Jeb needs to buy. And we're measuring this in feet. Well, we know that the area of this field is 7,728 square feet. How do we find the area of a circle? Well, that's one of our formulas from geometry again. The area of a circle is pi r squared. So the area of the field is going to be pi times, notice I picked r as the length of the pipe, pi times r squared is going to have to equal 7,728. To solve for r squared, I need to divide both sides of this equation by pi. So r squared equals 7,728 divided by pi. Using the square root property, I know that r has to equal plus or minus the square root of 7,728 divided by pi. Well, pi itself is a near rational number. I know when I take the square root of 7,728 divided by pi, I'm going to get a near rational number. Since this is really a real-life application, I'm going to go ahead and get a decimal approximation of this value for r. So I'm going to pull out my calculator and compute. I'm going to put this radicand in parentheses to be safe here. 7,728 divided by pi, close parentheses, and I'm taking the square root. I get about approximately 49.6. So r is approximately plus or minus 49.6. Here we're looking at an application problem in which r represents the length of pipe. So negative 49.6 doesn't make any sense. So if we have a pipe of length 49.6, is this going to check in that it covers the area of the field, which was 7,728 square feet? Well, for our check, if r is approximately 49.6, then pi r squared is going to be approximately pi times 49.6 squared. Again, I'm going to pull out the calculator for this check. So here I'm taking pi and multiplying it by 49.6 squared. And I wanted to get about 7,728 because the field was 7,728 square feet. This is off by a little bit, but I expected that because we only have an approximation for r. So now let's go ahead and write our conclusion. Uncle Jeb needs to buy about 49.6 feet of pipe. Maybe he's going to buy 50 feet because that's a little bit easier to measure than 49.6. But here's our approximation for the amount of pipe that Uncle Jeb needs to buy. Let's look at another application. A contractor is building forms for a foundation. He measures off 3 feet on a board and measures off 4 feet on another board. What is the length of the diagonal between the marked distances need to be in order for the forms to create a right angle? Well, let's think about a picture here. The contractor measures off 3 feet and then measures off 4 feet in another direction, and he wants these two boards to create a right angle. So we need to figure out what's the distance between the two marked distances. So let's let D represent the distance in feet between the 3-foot and 4-foot marks. Looks like we have a right triangle here. We can apply the Pythagorean theorem. The Pythagorean theorem tells us that 3 squared plus 4 squared equals D squared. Do you know what the answer is already? If you're thinking about those Pythagorean triples, you do. Let's simplify this. We have 9 plus 16 equals D squared. So 25 equals D squared. Using the square root property, I know that D is going to have to be plus or minus the square root of 25. So D is going to have to be plus or minus 5. Since D is representing a distance, though, -5 doesn't make any sense here. So we're going to choose D equals +5. I know that 3, 4, 5 is a Pythagorean triple, so I know that my answer checks here. So I'm going to go ahead and write the conclusion. The distance between the 3-foot and 4-foot marks needs to be 5 feet. This is a nice Pythagorean triple that contractors often use. If they're building forms or building walls, they can measure off 3 and 4 feet and make sure that the distance between those two marks is indeed 5 feet. Now let's find the distance from the point 1, -1 to the point 4, 5 in the coordinate plane using the Pythagorean theorem. So we're starting with the point 1, -1 and the point 4, 5. We're interested in this distance between them. We're told to use the Pythagorean theorem, so I need to think about a right triangle. Well, I can draw in a right triangle here using these as my legs. So if I let D represent the distance from the point 1, -1 to the point 4, 5, as shown on the diagram here, well, I can also look at the legs of this triangle, and I know this bottom leg is going to have a length of 1, 2, 3 units. And this vertical leg, that's going to have a length of 1, 2, 3, 4, 5, 6 units. So the Pythagorean theorem tells me that 3 squared plus 6 squared is going to have to equal D squared. So 9 plus 36 is going to have to equal D squared. So 45 is going to have to equal D squared. Now applying the square root property, I know that D is going to have to be plus or minus the square root of 45. Looking at this problem, this doesn't look very much like a real-world problem. This looks more like a pure math type problem. So I think I'm going to look at an exact answer instead of an approximation. I noticed right away that 45 wasn't a perfect square. Rather than approximating the square root of 45 on the calculator, I'm going to see if I can simplify the square root of 45. Does 45 have any perfect square factors? Well, sure, 45 is 9 times 5, and 9 is a perfect square. So I'm going to simplify this as d equals plus or minus the square root of 9 times the square root of 5. Simplifying further, we have d equals plus or minus 3 radical 5. D is still representing a distance here, the distance between the 2 points in the coordinate plane, so the negative 3 square root of 5 doesn't make any sense. Let's make sure that positive 3 square root of 5 actually does check before writing our conclusion. So all that I need to do is square 3 radical 5 and make sure that I get 45, which came from our 3 squared plus 6 squared. So when I square 3 radical 5, that's 3 squared times radical 5 squared, which is 9 times 5, which is indeed 45. So this checks. So I can say the distance from the point 1, negative 1, to the point 4, 5, is exactly 3 radical 5 units. And that concludes lesson 13.
What is